Hello everyone and thank you for joining us. In today's webinar, we will be discussing our products EMS and EMWorks 2D. We will demonstrate our simulation analysis solution for solenoids and actuators. Before discussing today's agenda, let me introduce ourselves. My name is Ehsan and I'm a sales engineer in EMWorks, and we will have my colleague Majdi, who is a senior application engineer in EMWorks. He will be delivering the technical part of today's webinar. Our agenda for today is the following. I will briefly talk about our solution advantages and benefits and what products we offer. Then my colleague will present the technical part. At the end of the technical presentation, I will talk about licensing, services, and various learning resources offered by EMWorks. The idea that lay behind integrating electromagnetic simulation software into a CAD tool is innovative and fresh. So the idea is, what happens conventionally is, if you want to use a new simulation software, you have to put tremendous effort and amount of time to learn a new modeling environment. First, and only after, you will be able to start your simulation. Furthermore, usually modeling features inside a simulation software is very primitive. It's not meant for complex geometry. So why don't you get the privilege of using most arguably best CAD tools in the world, either Solidworks or Inventor? Even if that is not the case and you already use your own CAD tools, so now it's time to import your model into your simulation tools. But what if you want to change different parameters and geometries and see the result on the spot? Yes, you should export and import a lot of times. You have to switch between two software multiple times to reach the optimum result. That's why it's better to do everything, modeling and simulation, all in one place. So that was the idea to address this issue. We are just inside your CAD tools such as SolidWorks or Autodesk Inventor. For example, for SolidWorks, which is the most powerful CAD tool with motion features currently, there were other plugins for other applications like mechanical and structural, but nothing for electromagnetic analysis. We honorably filled the gap, and we are offering 4 different products for our valid customer users and customers inside this CAD tool. Our products are gold certified by Dassault Systems SolidWorks Corporation since 2008. So we offer 4 products with various add-ons covering a wide range of frequency. Our first product is called EMS, which is used for electric and electromagnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, motors, and so on. The second product is EMWorks, which is used for electromagnetic simulation of RF, microwave, high frequency, and high-speed electrical and electronic devices. It covers applications including a wide range of antenna, resonators, filters, connectors, waveguides, and etc. Our third and fourth product, the first one is EMWorks 2D, which offers static analysis and covers the simulation of planar and axisymmetrical geometries. Our latest edition is Motor Wizard, which is a template-based motor design software. It offers analytical and finite element analyses for BLDC and PM motors. In addition to these solvers, we offer multiphysics solutions like thermal, motion, linear statics, and circuits. In today's webinar, we are talking about the EMS and EMWorks software to simulate and analyze solenoids and actuators. I would now request Majdi to take over and present the next part of this presentation. Thank you.
Thank you, Ahsan. Hello, everybody, and thank you all for taking time and joining us in today's webinar. In this session, you will discover the complete solution of EMWorks dedicated for solenoids and actuators. We will see together how we can perform electro-thermo-mechanical simulation inside Solidworks to solve the design issues that can be posed by these kind of applications. Before starting our demonstration, let's take a look on our agenda for today. In today's session, we are going to start with an introduction that shows some examples of solenoids and actuators. Then we will briefly talk about the main design issues of these devices. After that, we will present our proposed solution and see how we can use it to solve the design challenges and which kind of results we can get through some examples. And finally, we will end our presentation with a conclusion. So, solenoids and actuators are used in most of industrial applications, daily life devices, automotive components, aerospace and biomedical applications. As shown in this slide, we can see valve actuator, an electromechanical relay, voice coil actuator and MEMS micro actuator used in tactile display. These actuators are used to convert an electrical power into mechanical motion or structural deformation. They are applied to perform several functions like switching on/off an electrical signal and open or shut a valve. The main advantages of these devices are providing clean and fast operations. Some of the design challenges that can be faced while studying a solenoid actuator are computing the magnetic field strength and see when or where it saturates, calculating the different electromagnetic losses including eddy, winding and so on, and find out the impact of both eddy effects and any geometrical variable or parameter on the results. The most important quantities that need to be addressed as well are the created or the generated magnetic forces and in some cases the torques. So they are usually investigated for several parameters or versus several parameters like versus air gap, versus the applied current and the used material, for example. These forces are used to move a plunger from an initial position by counteracting spring force, for example. So the displacement, the speed and the acceleration are the quantities of interest here. So the complexity of such system increases when we add more components like spring, damper and friction contact to make the problem close to real life condition. The generated heat and the deformation caused by magnetic forces, especially in case of MEMS actuators, have to be evaluated as well. These are the main issues posed by solenoids and actuators applications. Due to the challenges or to these challenges which present some high level of complexity in some cases and to the increased demand for these actuators, engineers favorize the use of CAD design and simulation tools instead of the classic methods like analytical calculation, to meet their customer needs and requirements. These solutions represent as well powerful tools to design and build efficient and innovative products that can solve the most complicated issues and can be used in wider range of applications. In EMWorks, we develop several CAD simulation software that cover plenty of applications, including solenoids and actuators. In this demonstration, we are going to show you our complete solution to handle all the related design issues of these devices. EMWorks provides a full solution that can help designers to study and solve the different issues posed by solenoids and actuators. So our solution starts by offering a 2D and a 3D electromagnetic software covering both magnetic and electric fields. EMS is our 3D electromagnetic tool, while EMWorks 2D consists of a two-dimensional simulation software. They help to compute different results, including magnetic fields, forces, coil parameters, losses, etc. So at the earliest stage of the design, 2D analysis is recommended because it increases the productivity and the number of the design iterations, reduce time to market, and improve efficiency of final products. In addition to this, what makes our solution unique is being integrated inside Solidworks and Autodesk Inventor. These two powerful tools provide various modeling options to accurately and effortlessly convert your innovative ideas into CAD models ready for simulation. Multi-configurations feature of SolidWorks allows to test and solve different design configuration within the same model. This eliminates switching between several models to study different designs and to improve your system performance. So you reduce that switching between different designs, open, close the models. So changing from 3D geometry to 2D geometry is automated using 2D simplification feature of EMWorks 2D, and going back and forth is easy using EMWorks 2D. So we have a tool, or we have a feature that helps to convert a 3D geometry, a native 3D geometry, into 2D model ready for simulation automatically. So you don't need to create a 2D model manually. So just using 2D simplification feature, and through a few clicks you will get a 2D model ready for simulation. Another great feature that makes our solution more powerful is the coupling to SolidWorks Motion. This SolidWorks Motion is full of features and options. You can have a spring, damper, friction contact, gravity force, linear and rotary modes, and so on. You can also do many plots and so on. So EMS allows to couple your magnetic study to a motion analysis where you can find spring, damper, and more components. So this makes your problem or electromechanical problem more realistic. So once you couple your EMS study to SolidWorks Motion, EMS internally communicates with SolidWorks Motion to exchange the needed information like position, force, and more. So at the end, EMS generates both electromechanical results, including position, or the position of your moving parts, the speed, the force, etc. Besides the motion coupling, parametric studies can be performed as well to cover the different design scenarios, like computing the force versus air gap distance versus angle versus the input current, materials, and more, and many other variables. We may use SolidWorks distance and angle mates, sketch dimensions, and more inputs as design variables. So losses in electrical devices are converted into heat, and this can damage your device or affect their performance. It should be carefully estimated and minimized as much as possible. EMS comes with embedded multiphysics capabilities, including thermal and structural solvers. So you just need to check a box to enable this coupling, or one of this coupling, or a combination of them. Then define the thermal boundary conditions along with the electromagnetic setup. So there is no need to export or import any data. This ensures a fast and easy workflow. So MEMS, in case of MEMS actuators, which are based on structural deformation caused by magnetic forces, EMS allows to study this type of applications through its embedded structural solver. So we can compute the deformation caused by magnetic forces in this actuator using EMS magnetic coupled to structural solver. So finally we can see that EMS helps to answer most of the design challenges which can be raised when studying solenoids and actuator applications. So in what's left of our demonstration, we will have a look on a couple of examples solved with both EMS and EMWorks and see a deeper view of our solution. So our first example consists of an axisymmetric actuator made of ferromagnetic core, plunger, and a yoke plus a stranded coil. However, the original model has a 3D geometry, but it can be solved with a 2D simulation to save time and accelerate the process. The model is converted from 3D to 2D through 2D simplification feature of EMWorks 2D, which is our 2D simulation software. It takes only few seconds to get a model ready for simulation, define the setup, and get results as you can see in this slide. Different plots of the magnetic fields are shown. The 3D original model is not eliminated or deleted, it is still there. That's why we can superimpose the 2D results with the 3D geometry. Any geometrical dimension or a parameter defined in SolidWorks can be added or defined as a variable parameter in EMWorks 2D. So a parametric study is defined to compute the force versus different air gap distance. As you can see in the top right figure, the force decreases when the air gap distance increases. This kind of studies helps to estimate the force at different positions of the moving plunger. So after that, now we fixed the air gap. So we put the air gap at a specific position, which is 2 mm, while the coil current is varied. So unlike the air gap, the force increases with the current. This is a second type of analysis that can help us to estimate the force versus the coil current. A second example that we are seeing is also an axisymmetric actuator, but now we will use EMS 3D and SolidWorks Motion to solve this example. As we mentioned earlier, SolidWorks Motion allows several options and features that can make simulating such problem possible and realistic as much as possible. In this example, we are going to see the results when DC and pulse excitations are applied under the presence of spring and damper in SolidWorks Motion study. In the left figure, we can see a typical settings of a spring. The defined spring is used to revert the plunger to its initial position when the excitation is turned off. After setting up the motion study, including the force that will be computed by EMS and the spring, here we used only a spring. So an EMS transient magnetic simulation, it's time domain simulation, coupled to this motion analysis is performed. So we created a motion study, then we defined an EMS study, transient magnetic study, and do the coupling between them. So EMS computes both magnetic and mechanical results and communicates with SolidWorks Motion. Few results here are shown in this slide. They are the force results, so we can see the force results, the displacement, the speed, and the acceleration of the moving plunger. So we have the magnetic force plus some mechanical quantities. all the results show few oscillations. So we can see that there are few oscillations before reaching their steady state. So the plunger became stationary after a certain time, and once the equilibrium between the spring and the magnetic forces is reached. These oscillations cause some vibration and a non-stability of the system. Now we want to investigate the results when a damper is activated or added in this motion study. So we have, in addition to the spring we defined it earlier, we added a linear damper. So as shown in these graphs, the oscillations are almost eliminated. So once we add the damper, the oscillation are removed, are reduced. So this helps to have a more stable system. So as we saw, so we are able to combine both damper and spring in one motion study using EMS and Solidworks Motion coupling. A third case we solved consists of applying a pulse current instead of DC current. So earlier we applied the DC current, constant current. Now we are applying a pulse. So we can see that in case of the damper is disabled, so damper is removed again. When the excitation became zero, the system doesn't reach its equilibrium. So as you can see, the system, when the excitation is switched off, there are a lot of oscillations. So the system is not, or the plunger didn't get back to its initial position. So it continues to oscillate, which is not the case when we enable again the damper. So when we enable the damper, so the system is stable when turning both on and off the excitation. This kind of analysis helps to study the behavior of the system under several conditions and find out the right parameters of the spring and the damper. So through these simulations, we can solve our system by adding spring, damper, or whatever you want, and also it helps us to specify or study and design your spring and damper parameters and settings. So you can see as well some animation of the plots. So you can see at the top this animation of the field when the damper is removed, so it continues to oscillate, and the second one, as you can see, it's more stable and it reaches its steady state without oscillation. Then when turning off, it goes back to its initial position. Another analysis is performed to see the impact of varying the current on the results of the force and the maximum displacement. So now we vary the current to see what impact of this quantity on the force and also in the maximum reached displacement. So as can be seen, both quantities increase with the current. A third example consists of an electromechanical relay that is used in several industrial and domestic applications. In this analysis, we run a parametric simulation where the angle between the moving armature and the ferromagnetic core is the variable, since we have a rotational motion in this case. So here we have like a rotational motion. So the armature is rotating around its axis. So both the force and the torque results are computed versus this angle, defined angle. We can see that the force increases when getting close to the core while the torque decreases. So an animation of the magnetic flux versus angle is shown as well. So as you can see in the right side, that some animations of the field versus different angles. Now we come to our last example, which is a voice coil actuator, where the coil is the moving part. So some fields plots are shown in this slide. As you can see, this is a third or a fourth example, which consists of a voice coil. The moving part now, the moving part of this voice coil actuator is the coil, not the magnet. So these graphs represent the Lorentz force results versus several variables. So we can see the results of the force versus both current and coil position. From these results, we can compute the force sensitivity parameter, which shows that the force of a voice coil actuator is constant for a wider range of stroke, which is opposite to the case of the plunger. So at the right side we can see as well the back EMF results and the sensitivity parameter of the back EMF versus different speeds. The force is now investigated for this kind of problems, so versus time and versus different applied voltage. So now we are applying voltage or different voltage rates and check the impact of these voltages on the force and the coil position and the speed. So the force increases with the voltage, as can be seen from the left figure, and each steady state time depends on the voltage as well. So each voltage or each applied voltage has its steady state force, I mean time. At the right side we can see both linear displacement and speed versus time, and at different applied voltage as well. So the coil can reach its maximum stroke in a lower time when the voltage is high. So we increase the voltage, we can increase the voltage to get a higher force, then a higher displacement, and maybe accelerate our the motion of the coil. A thermal coupling analysis is performed. As we mentioned earlier, that in EMS we have the possibility to couple our magnetic or electric simulation to thermal or structural or a motion or a combination of them. So here we run a thermal coupling analysis to get an idea about the heat generated because of the copper losses. In this case we have only losses coming from winding, so no core loss, no eddy effects, so everything is turned off, so only winding losses are taken into account. So these losses increases with the applied voltages, so the higher voltage, the higher the losses are. So, and this leads as well to more generated heat, as we can see from the right figures. Once we have high current or a higher current or high voltage, we will get a higher temperature. So we need to find out, so as a conclusion, we need to find out a trade-off between increasing the applied voltage to get higher force and maximum displacement and keeping the heat at low levels. So using this kind of simulation, we can find this trade-off. So through these simulations, we can conclude that both EMS and EMWorks 2D covered all the design issues that can be posed by these applications, I mean solenoids and actuator applications. Now, and before we end our presentation, let's quickly have a look on EMS and EMWorks 2D on their environments. So now we are inside SolidWorks. As we mentioned earlier, that both EMWorks 2D and EMS are fully embedded inside SolidWorks. So as you can see, this is EMS tab and this is EMWorks 2D tab. So this is a 3D model. So we created this 3D model. It's an axisymmetric actuator. Let's do a cross-section view and see what's inside. We have the yoke, the core, the coil, and the moving plunger. So we can perform parametric analysis by parameterizing the distance between this plunger and this core, and we can as well run a motion analysis for this application. So let's check EMS tab, or let's go to EMWorks 2D tab. So you don't need to recreate a 2D model if you have a 3D geometry. So you don't need to recreate the 2D model. You just define local coordinate system like this. So we have an axisymmetric problem. So as you can see, you should define this z axis along with the axis of the problem of the model, and put x axis in the direction that you wanna cut your model. So this one, and go here, then use this feature. We mentioned this feature. It's a 2D simplification feature that helps to create a 2D model. Let's choose the symmetry type. It's axisymmetric. Then select this coordinate system, then validate. The software will create a 2D geometry from this 3D geometry. Will do like a cut of your model or extract a 2D model from the 3D geometry. You don't need to perform any other steps, and you won't lose your 3D geometry. So you will keep using the 3D geometry. So this is our 3D geometry, as you can see, and we have the surface created as well. So we can have both 2D and 3D geometries in the same model. We also may use this option, show 2D. Let's show the 2D model. I already performed the 2D simplification, so I'll just show the 2D model that I have created. This now we can see our 2D geometry. So we have also this outer region, this air and so on. So as you can see, this is our outer region, outer air region. After that, you just need to create a new study. Go here, define the type of the study. We have magnetostatic, electrostatic, and transient magnetic. You can choose this or check this option of parameterization if you want to parameterize whether geometrical or simulation variable. We have also, in case of rotation or rotational models with a rotationally motion. So if you want to do rotational motion, you can add this or check this option, so you can perform a rotational motion. And the coupling to circuit is available as well in the transient magnetic, so you can create a schematic with and define several components like diodes, inductors, switchers, and whatever you want. So there you choose as well the local coordinate system for your problem and create your study. Then you will have this tree, what's called EMWorks tree or EMS tree. It's the same for both software. So you start by defining the material. This is the list of the material. You can use this option. For example, apply material. You will open a rich and well organized material library where you can find any material you want, or you can create or edit your material. So you can add a new material to this library or edit the existing material. So you can perform these two tasks. After that, you define the boundary conditions, starting by this condition: magnetic vector potential set to 0 in the outer edges of your problem. Then create your coil if you have a coil, or if you have a magnet, so you can run the minimum required excitation is a coil or a magnet. So you can also define where you want to compute the force, whether a force or a torque. So let's see here. In this example, we are interested, or actually for axisymmetric, we only support force calculation. When we have like planar problem, we can perform or we can compute both force and torque results. So we have the parameterization section where you should add your parameters. So this is our added parameters. So I added this parameter as already. So we can use global variable from SolidWorks as well. Then define this. So we have geometric variables. So this is our variable, then the value, mean, max, and step, and run your simulation. So let's check some results. For example, so we have this part is hidden. Let's show it. Okay. So this is the magnetic field results of our problem, and we can switch between the scenarios. Okay, so this is concerning EMWorks 2D. Let's move now to EMS. So using the same model, we can do 3D analysis. So, and I want to mention something, that in case you wanted to change any dimension in the geometry. So this change is automatically converted for both models. So if you change in 2D, you will get this change automatically in the 3D, and the same thing in the opposite way. So if you change in 3D, you will get the change or the edit in the 2D model. So you don't need to duplicate this work. Let's go to EMS tab. So same structure, same tree. We have the list of the material, the list of the boundary conditions. We have this. You can define the coil as well, force and torque, the mesh section, and so on. But so unlike EMWorks 2D, we have more modules in the 3D. So let's try to create a new study. Okay, so we have 6 modules. We have 3 for electric simulation and the 3 for magnetic simulation. We have parameterization option, and we have more coupling or more analysis or multiphysics options. So we have thermal, structural, motion, and circuit coupling. So and we can choose one of them or combination of them. So if you want to solve a thermal simulation, you can check this option, then create a new study. You can for this option as well, we have steady state and transient. We can perform steady state thermal or transient thermal simulation. We have the structural option as well, motion and circuit. We can choose a combination of them. So we can have like thermal plus motion, or thermal plus structural, or circuit plus motion and plus thermal, and so on. So this is possible using these options or these multiphysics options. So we have this meshing tab. So we have 2 options. We have manual meshing. So the user has the responsibility to define the mesh. He can define mesh controls, he can play with the settings, and so on. And we have the second option, which is called adaptive meshing. So we define some settings and let the software run the simulation and creates the mesh depending on the results. So you don't need to worry about the results accuracy if you choose the adaptation option. So you should get the most accurate results depending as well on the settings you put. So if you reduce of this error, you will have more accurate results. So this basically about EMS. So as we can see here, so I already solved this study. We can show some plots. Let me go back and show the 3D model. It's showing the 3D model and hiding the 2D surfaces, and we can have both of them at the same time. Okay, now this is our 3D model. Let's hide the air and the band. Go here. Okay, we have several plot options. We have a fringe, vector, streamline plot, and 2D plot. So let's try to see a fringe plot. This is a fringe plot. Okay, so as you can see, this is the plot of the magnetic field. Let's see a vector plot. So this is a plot of the magnetic field with a vector plots, and we have this option of streamline, the most interesting options. We have the lines, the field lines here. So as you can see, these are the magnetic field lines. We have some options here to play with these lines. Okay, so this concerning this plot results, and we have this tabular results. They should contain results related to like force, torque, inductance, resistance, and so on. So related to coil. Okay, now let's have a look on the motion study. Okay, Open this SolidWorks Motion study. EMS can be coupled, or EMS studies can be coupled to motion analysis, not animation, not basic motion. So we should add this from the add-in of SolidWorks Motion, as you can see. Okay, let's choose motion analysis. So in case we want to couple a basic magnetic simulation to a motion, so we have the option to define a force or motor or a rotary or linear motor. So if we define a force and we want to EMS computes the force, then sends it to SolidWorks Motion and get the displacement from that. Or we move something and compute the results. It's like parameterization. So if we want to rotate or translate something, and at each position EMS computes the force. So there are two types of motion analysis. So we have a torque or force-driven motion or a motor-driven motion. So here we have a force-driven motion. We define a force where we want to compute the force and put 0. It's 0 because EMS will compute this force and sends it to SolidWorks Motion. So here let me do a section. So in case I want to add a spring, I just choose this option, spring, then choose where I want to define this spring, like here for example. I can play with these settings. I can define also a damper, so I can define it from this page, or we can define it from as a separate setting or a separate option. So let's for example validate this. We have as well this option of damper, so we can define a damper between these two components. And this option, so like this. Okay, so and you have this damping constant, and that can be modified. So combining all these settings, EMS will compute the force, then SolidWorks Motion uses that force, then convert it into in addition to what is there, like spring, damper, maybe gravity option, maybe linear initial velocity or whatever, and combine them to compute the mechanical results, displacement and maybe speed, acceleration, and so on. So you can plot also the mechanical results using this plot options. So you can choose whatever you want: displacement, velocity, force, and other quantities. So that's all. So this is basically EMS and EMWorks 2D inside SolidWorks. We have this magnetic simulation, and in addition to magnetic simulation, we have a few multiphysics options that can be added. No need to export or import any data. As you can see, just a checkbox where you can, from where you can enable multiphysics option and solve your simulation. So that's all you need. Okay, so let's get back to our presentation. Okay, now back to our presentation and its last part, which is the conclusion. So EMWorks, both EMWorks 2D and EMS were used to solve a couple of solenoids and actuators applications. Magnetic fields were estimated for both 2D and 3D geometry. Force and torque results were calculated versus different variables and using parametric analysis. Displacement, speed, and accelerations were predicted using or through EMS coupled to SolidWorks Motion. Spring, damper were included in the simulation as well. So thermal analysis were performed at the end to compute the temperature results of a voice coil actuator. So thank you all for your attention, and I hand over again the screen to my colleague Hassan to continue this presentation. Thank you.
Thank you, Majdi. Thank you everyone for bearing with us, and I hope you have learned enough from this webinar so far. Let me briefly touch upon the licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup programs. Each program has its own benefits and requirements. Within the commercial program, we offer perpetual or lifetime licenses, while our licensing structure is usually annually based on the rest of the programs. We have a combination of free and paid licenses for students, academics, mentors, lecturers, and professors based on the program they choose. And for startups, we are offering a very interesting plan for paying in installments. For the learning resources, EMWorks offer various free learning resources. With the software purchase or trial, users can access to the demo viewer section of the software, through which they can access many predefined, ready-to-solve models and examples and tutorials. In addition, we have regular webinar series on trending electromagnetic topics. Moreover, we post several application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all users of EMWorks software. Our support service is the strongest point that I can mention in this presentation. We always have your back before and after sales. That is including one-to-one web demo sessions to shorten your learning curve, or even do benchmarking with the model that you shared with us. Also, we offer consultation and design engineering services. Even come up with a new design as per your requirement, or refine and optimize your existing design. These are only a couple of our valued clients. These big names are coming from different industries, showing our comprehensive and extensive solution. At the end, I encourage everyone to try our software and experience its capabilities. We offer 2 weeks of free trial access. Visit our webpage, emworks.com, go to our contact page, fill in your information to submit your request, and we will contact you. At the end, I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you very much, and have a great rest of the day.